with the first cohort of students with their thesis, as well as we are gaining good results with the thesis that the second cohort is going to complete right now. We are honored to participate in your conference in Abu Dhabi. We have been your guest for 2 times. We have participated as a member of the scientific committee, and we hope to meet you again in person in Rome or in Abu Dhabi or in London, but in person, because nothing substitutes the human relation. So thank you again so much, not only for your cooperation, but also for your expertise and for your friendship. You are a wonderful person, and we are very happy to cooperate with you from my side and from all the staff side.
Thank you very much indeed.
Michael.
So now we are going to change the emphasis slightly, because you cannot run such a wonderful conference without some financial support. And in fact, we have a platinum sponsor here and a gold sponsor. We have 2 companies that are going to present their company work. If you haven't had time to go out and have a look, please do so. You can contact them. And if you have interests, I'm sure they will be happy to supply that information. So for the first one, we have BMD. And I'm going to leave the floor. I'm not sure who to.
I know that Dr. Carcano is with Dr. Pinciarelli as well, and they will run the presentation together. Dr. Carcano is the CEO of the company. Let me point out a couple of words about the company. BMD is Italian provider of detection technologies for CBRNe, and they work with the Prime Minister Office, with the Ministry of Defense and Ministry of Interior, among the other entities. And I had the privilege and the pleasure to work with them in 2011 and 2012, and we continue the cooperation in this way through university company cooperation. I kindly ask to Ricardo to make a check of the microphone if it is working. Ricardo, are you there?
Yes, I'm here. Can you hear me?
We can hear you very well, but we cannot see the camera. Is it okay? Great, we can see you as well, so we leave you the floor. Welcome, Dr. Riccardo Carcano. Thank you for sponsoring, as a platinum sponsor, the conference. We do invite you also to see the record of the video of yesterday, because you will find another presentation in Technical Table 1, Day 2, about the technologies of BMD, and today there is another interesting presentation. I do not want to steal more time. Ricardo, you have the floor.
Okay, let me see how I can share my computer.
We're already sharing. We see your PowerPoint.
Efficiente.
No.
Il tasto schermo intero, quello in basso. Quello che fa andare alla presentazione.
Just a minute, sorry. Are you seeing my computer now?
Yes, it's full screen.
Good. We will make a very short introduction to our company, and then I would like to leave everything to Luca, who will introduce something that might be quite interesting for the days we are facing right now. So you already introduced BMD. The company was founded in 1994, and we have been dealing on several projects with the Ministry of Defense, Ministry of Interior, and for more than 20 years we have been involved in introducing new technology into the Italian market, and by doing it, we had the ability to also make a dedicated integrated system for various solutions. Our main field of activities are safety and security for checkpoint, critical infrastructure, post office, and special application. We are deeply involved in filtration for industrial, civil, and military application. Our core business is chemical, biological, radiological detection and protection, and we have been more and more focused on SICC environment by including different technologies, different procedures to help the SICC requirement. And the last sphere of activity that has been added to our company are special projects where we are mainly dealing with robots, UGVs, UAVs, and since we are dealing with UAVs, also special anti-drone systems. This is just a quick picture of all the companies we are dealing with, our partners in a different project, multi-year project, by the way. And our main customers are all the Italian Armed Forces, Ministry of Interior, the Vatican, the Red Cross. This is a problem we are quite often facing because everybody is thinking that we are dealing with a weapon-like system, which is not. And so we are emphasizing that we are also dealing with, again, the Vatican, the Red Cross, and other agencies which absolutely are not under the war environment. I would like to skip the main activities we are carrying out because I would like to be mainly focused on what was the scope of our attending the symposium that was planned in 2019, and we were planning to introduce this system developed by Battelle in the States for biological identification. Then, because of course the pandemic stopped the seminar in April, we are right now here with just the presentation of the system, and we have many ongoing dialogues with several organizations that would like to adopt a system that was developed to face CWA's agent in a sort of war scenario and develop the techniques to the ability of detecting also the coronavirus in the hospitals or other environments. So the system is completely automatic. It's a biological air sampling system and identification system. Out of it, I would like to leave, and they are the projects that we have been focused on, like UGVs for SICC and naval system, but they are traditional CBRNe detection system. But I would like to leave the word to Luca, who will introduce you the REMS concept and the real machine which we have here on the table, and hopefully we will have the opportunity to show you. Now, I have to... Okay. Can you see? Okay, now you can see the camera. And
Riccardo, you want just the camera without the screen?
yes.
Okay, so I can remove your screen of the computer, okay?
Yes, but later on, after Luca will introduce the equipment, I will need to have the screen again.
Then I will give you the screen again. I will just remove for now, okay?
Okay.
So we have your camera as a full screen. Okay, now you have the camera as a full screen.
Okay. So I will introduce briefly the system, and probably you can hear me. Okay, I will remove the protection here. So briefly, this is REPS, Resource Effective Bioidentification System. It's like you can see, it's a self-contained system. Everything we need is in this box, in this sun yellow box, with the black sampling line that you can see here. And just as a main description, we have on this side the battery compartment that we can open easily and show the three batteries we can remove or we can plug. This is the battery compartment. Obviously, the system is sealed. This is the front panel of the unit. I can open it safely because the system is off, and you will see what is inside. It's very important here. It's the cassette, the tape cassette where the sample, the air sample is gone through and all the particles are collected. And it's this white piece of plastic here. Inside we have electronics, the internal computer with the proper OS inside, and we have the Raman microscope, which is here, and we have the capability to sample the air from the inlet stack, which is this part of the REPS. So the particles are going inside those rings, are going inside the tube, and are collected by the electrostatic force, the Coulombic attraction in the metal tape inside the cassette. And all is done in a sealed way. So normally it should be closed like this, with the front panel closed. And so the air is coming in this way, and here it's the outlet. On the rear part of the unit, we have all the connectors for power, Ethernet, the med station, USB port, and obviously we have what we call the connector for the alarm for the sounder in case we have a positive detection. So this is briefly the REPS. Also, we have another option that it's not shown here in the real unit, which is an adapter that we put here. We remove the air sampling stack and we put the liquid injector. So we have an optional unit here, so we can inject a liquid. We need few microliters, so we will create an aerosol of our liquid, so we can detect all the bioagents, not only in the air but also in the liquid phase. And when we say liquid phase, can be rain, can be a puddle of water, can be anything. We can take water from a toilet, from whenever we want. So this is a very briefly and really simple explanation of the REPS. We can run the system via the front panel. So I don't know if you can see, but we have the main switch here, just few panel. We can change the sounder in case of detection of the light of the keys, the keyboard, but we can interact with the system also with an external computer provided with the Ethernet port. So this is almost the explanation for the REPS.
Andrea, can you share the video with us, the monitor with us?
Yes, I will give you the screen again. Just 1 second. And here you have it.
Okay.
Now you can share the screen.
No, come vuoi. Vabbè, non fai così.
Okay. Now we see the screen again.
Okay, so and now I will go through the standard presentation like the one we did yesterday for the catalytic filter. So it is a brief presentation. Maybe some of you already saw it in other international events. So in case you have questions, just feel free to ask. So the first, it's about Battelle, and okay, we don't have so much time, but you can read through the lines of the main points. And you see 20,000 people, 20,000 people. and over 5,000 projects, blah, 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 more than 150 locations, and some are international ones. And we were lucky to visit the main institution in Columbus, Ohio, and also we went to the field campus where they are doing all the field activity for chem, bio, and explosives. A really nice experience in case you can do it. So we go to REPS. So I do remember again the name of the unit to you. It's Resource Effective Bioidentification System. And we have a first question mark, which is why REPS? And it's REPS because we need something that is working easily in the field, especially for military units, for firefighters, for asthma teams that cannot have so much time, and they are not really field biologists or forensic personnel. So if you remember earlier, I was mentioning to you that we have a computer, and so in this case it's a Panasonic Toughbook, but can be anything you like, and you can have an idea about, a very general idea about the software. So we can duplicate the keyboard in the real system, and also we can see the answers, the results. Obviously, being an Ethernet connection, we can log tons of different reps within one simple GUI. So we can manage like a network of many reps. So we will go to a system description, some general data of the testing phase we did in the past. So this is why reps, there are so many points. The key points in our mind is like no consumable liquids, autonomous operation, and near real time. We say near real time because we are looking for aerosols, bioaerosols. So we need to collect the sample. And I can tell you that the regular method can be anything from 15 to 30 minutes. And when I say regular method, I do intend sampling and detection. So it is not real time, it's near real time. And you see IDs, identities for BWs and CWs, obviously aerosols phase, not for vapors and gases. Obviously, Battelle has the capability to increase the spectral library within very few hours. We are stating 24 hours, it can be even less. Low false alarm rates, you will see some tables later. Non-destructive analysis, it's a molecular spectroscopy, and I heard a lot of work that were presented about Raman, so you already know the theory behind, and we will not lose time. And if we run the system with batteries, we have not less than 12 hours of continuous batteries. And obviously, we can archive the sample. I will show you later. And this slide is very simple. It can be complex to understand, but it's what it is at the moment. You see from the top left what was and what it is somehow the standard in some countries like US. It's a huge trailer with the power supply, the system and consumables. You need 2 people, and the estimation of the cost is roughly $1,000 per day. We went to the JDPDS, which was the 2000 solution, smaller, a person only, but the price was roughly half price of the bits. And today we are proposing reps. You saw the system. It's like 50 by 50 by 50, maybe a little less. We don't need any people, and the price for running the system is roughly $1 per day, because we are just considering the price of the tape, the cassette tape, and we can run thousands of analyses with a single tape. Here we have a little bit about theory, and maybe it's late, it's time to go to lunch and finish the first half of the conference. And so you can read through the lines. What is important is that it's a Raman spectroscopy, it's a molecular spectroscopy. Oh, okay, you are familiar with benchtop Raman systems for explosives, warfare agents, and for forensics. And now you know that the chemistry is not looking if the molecular weight is 100 or 1,000 or millions of Daltons. So in this case, we are exciting the molecules, the atoms, in the same way that we are doing for small molecules. So we have the same principle behind. We have a laser, we are going through the excitation, and so during the relaxation phase, we are getting what is called Raman shift. Very important. We don't go through molecular biology, so we don't need primates, probes, reagents, substrates, whatever. We just need the cassette tape, which is a metal sheet inside the plastic container, full stop. Okay, you see here a real spectrum from Bacillus subtilis. Time is running fast, so don't want to spend so much. Or in comparison with the regular Raman spectra, you see a lot of peaks because of the molecule. It's quite complex in comparison with a single benzene, toluene, sarin, or whatever you want. So much more peaks, much more signals to interpret and to identify. Oh, we have a video here. I'm not sure we can run it. I will try.
Luca, the only thing is that the audio do not pass, so you have to comment with your voice, please.
Yeah. Thanks, Andrea. So you see, this is the previous version of Red. So you saw just the cassette. So this is the airflow part. So the aerosol is going from the inlet stack to the metal tape via electrostatic attraction. The particles are sealed on the top of the metal tape. And you see here the virtual process. When the sampling is finished, it's going to start the Raman acquisition process. So there is like a Raman microscope. What you see, like the black spot, is the spot that was sampled in the previous phase. So the Raman spectra are going to be acquired, digitalized, and checked by the reference database. All the process is done within the black circle, and it is done automatically, and the identification can appear in a few seconds or in minutes, depending on where the laser probe will excitate the molecular spectroscopy. So you see here the virtual process of populating the acquisition, and this is done automatically by the system. In other words, the operator doesn't have to do anything, just see what is going on. And okay, this is the full spectra and comparison with the database. And at the end, you will see the final result. From an operational point of view, you don't have to need anything about spectroscopy. You will get the result via a sounder, via a LED, or through the Ethernet port to the computer with the name of the agent. So you see that the sampling stack a little bit different. On the rear side, you saw also the antennas, because we have also the option for the Wi-Fi system. So this is the part of the movie, and we continue with the presentation. Just in this case, this is the detection process that we are running. We have 3 steps. We don't have to run all the steps. We start with the first, and it's a classifier. If we have a carbon-nitrogen bond, we are going to the second step. If we have also some heteroatomic parts of the molecule, nitrogen, phosphorus, sulfur, it's probably a bio, and so we will use like 10 seconds, and at the end, we will have the identification step, which is 50 seconds, so in total, it's roughly a minute. So first step is looking for the carbon-nitrogen bond. The second step for heteroatomic bonds for seeing if it's bio or not. And if it is bio, we will go to the final acquisition of the Raman spectra and in spectrum. And in this case, we will take roughly 50 seconds, so a minute in total. We see some data that are coming out from the trials we did. If you see, we started in 2009, and some others are still running. Obviously, the ones that started at the military facility were closed and started for other. I don't want to lose too much time here, but you can read through the lines, and you see somewhere in June 2009, CW ID feasibility. So it was demonstrated also for the warfare, chemical warfare agent. You see here something that was collected during a test, and no aerosol, blah, 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 blah. Okay, don't want to lose time here. And this is quite interesting, since these trials were done under the US government. So they selected 3 different systems that are shown one after the other, starting from the big red case that you believe is something related to the power lines, which is in reality a biodetection system. It is someone that was mentioned in one of the first slides. You see the first prototype of REX, which is in the middle, and you see another system on the far left, which in a metal case. So there were selected 3 systems, and with a duty cycle of roughly 30 minutes, starting from temperature from -10 up to +50 Celsius. And those systems were spread in 3 metro stations in Boston, and they were releasing, the US government was releasing simulants. Obviously, the competitors didn't know when, how, and what was the simulant. And on the bottom right, you see the distance between the metro stations, and from the 2 farthest, it's roughly more than 2.5 kilometers. And those are the final data. You don't have to study or read all the data. What is really important? Try to see the last column. And the REX was able to run roughly 6,000 samples, was able to identify roughly 3,005,000 particles. Of those, 15,000 were with carbon-hydrogen bond, and of those, roughly 500 were biological particles. 56 of these 500 were identified of simulants, and no one was identified as a real BW agent. So this leads us to conclude that we get the 0 false alarm rate. That in biosystem, it's very, very, very important. Now we are telling you that whether you trust or not Raman spectroscopy, when the system is it's going to alarm because it's identified a biological warfare agent, it's going to chat to create a sample that is done automatically by the system, and it's collected in a small vial, in a small plastic vial that is installed just behind the front door of the system. So you can put REX in standby mode, put in a clean area, open the door following the procedure for the laser safety, remove the plastic vial, put a cap, and send it to a forensic lab or to a field lab, or to whatever you want to confirm with standard molecular biology techniques. So we are going through the end. We have the benefits, the special features. You can read it. What is very important in my case, it's minimum cost for running the system, minimum false alarm rate, roughly going to 0. In the field, it's continuous, autonomous, it runs for at least 12 hours with full charged batteries. Obviously, you can run on house power, and it's forever unless you finish the cassette tape. And obviously, in case of positive detection, you get the archival sample to check with the PCR or whatever you like. And this is probably the last screen I have to share with you, and this is coming from what Ricardo anticipated you earlier. So those are the preliminary findings that we had with the REX. So we already tested in some medics and hospital environments. So we were able to demonstrate, differentiate SARS-CoV-2 from other coronaviruses, which is quite difficult because most of the biological aspects are quite the same. And we were able to measure the virus diffusion by patients that are together. We were able to detect COVID in air, close to the system, to the patients, and in the HVAC system. And also we were able to detect in the same way of the traditional sampling system coupled with the PCR time, with the PCR method. So, and obviously, as like a scientific, with a scientific backup program, we are always saying, oh, we need additional studies. Obviously, we can say that we can detect SARS-CoV-2 in the air. And so this is the end of the presentation.
Thank you, Luca. Thank you, Ricardo. And we have a couple of questions from the audience. The first one, but I think you already answered, is how fast is this technology? Is 15 to 30 minutes. So I heard from one slide.
Yes. 15, okay, sorry.
No, please.
It's 15 to 30 minutes as a standard method. We suggest not to sample less than 5 minutes, so detection will take 5, 10, 15 minutes, but you can run it on a continuous basis. So whenever it's sampling the first sample, the second sample, you can analyze the first. But anyway, you said correct. Yes.
And the second one from Dr. Konstantinovsky of German Space Agency is what concentration can you detect with these instruments?
We can detect anything from, if I remember well, 100 particles per liter of air. This is the minimum detectable limits. And let's say I don't know the actual figures for SARS-CoV-2. If this was the question. So I can give you just the general detection limits, not specific for the SARS-CoV-2 virus.
It was a generic question, so the answer is perfect. Thank you.
Okay.
I cannot see other question from the audience. So, and okay, the other question is how it works in case of mixtures of substances. The question is from Dr. Peterfi from the OPCW.
Yes. Let's do it this way. We use a Raman database. We use a Raman spectral database. And you know that from a purely technical point of view, we have hundreds and hundreds of different potential biological agents. So we have to distinguish if it is for field BW detection, if it is for a general military use, for very important places to monitor, or for microbiological point of view. So if we go with a dedicated spectral library, we have a few agents, like the BW spectral library for few agents. And by memory, it never happened that you can have agent A plus agent B at the same time. Normally, you have one per time. If you believe about the chemical, it's completely different. But you need to have them in the aerosol phase. So if you have in mind like hydrogen cyanide and other like nerve agent, you won't get anything for the hydrogen cyanide because it's not an aerosol, it's a vapor. It's not in normal condition.
Luca, thank you so much. I think that you completely answered to the question. If I have not now in the chat, but if we will receive more question, I will send to you and Ricardo. And again, I invite all the participants to go in the industrial exhibitor of BMD, which is in the first floor of the virtual reality. You can see their video, download their brochure, you can gain their contact, and you can talk also with them or organize a conf meeting with them to talk about your interest in their technologies. Thanks again to Dr. Pinciarelli, to Dr. Carcano, and to the BMD to supporting us. And I think we can give the floor to Dr. Giovanni Longo from the VUEL-GOR.
Hello, good morning.
Good morning and
good afternoon or good night, depending where you are.
Michael, please, I leave you the floor for an introduction.
Yeah, right. Well, WO-GOR Association. Everyone's heard of Gore-Tex. Everyone must have something. Either you own it or at least you recognize it. But they do so much more and have done so much more. And we're now going to get some introduction and some information about their protective fabrics, and in particular the new technologies that they are using for individual CBRNe protection. So, sir, the floor is yours.
Thank you.
Let me just thank for 1 second Gore to be our golden sponsor and supporting the realization of this conference. Is thanks to you guys, basically, if we are here and we are connecting all the world. And again, I do invite everybody to visit the stand in the virtual reality of Gore, because you can do the same work. Look at the video, download the brochure, and start an interaction with Giovanni, with the colleagues from the Gore for any needs that you have for protection, but not only technologies in CBRN. Giovanni, you have the floor. Thank you so much.
Okay.
Dr. Carcano is not connected. I don't. Yeah. Okay.
He joined right now.
Okay. Probably I ask after to. Okay. Here, last presentation by Luca Pincerelli that present BMD company and research made by BMD. I many thanks to BMD company because it supported the conference as platinum sponsor. Thank you very much for your support, and if you want, you go to presentation.
Thank you, Professor. I hope everyone is able to listen to me. And so I will present the outcome of research and development program that we run for almost like four years. And so you see the Ministry of Defense, which is in Italian Ministero della Difesa, is the ministry that supported us with funding the project. Obviously, it's our company, which is BMD. And also we joined with other two companies which are leading the activity. One is Chericol and the other one is Colorobia Consulting. So altogether we were a unique team developing what we realized. So it's an air filtration and purification system for CBRN applications based on nanotechnologies and photocatalysis. So this is the main layout we are running, and I will try to be very fast and not go into deep details, just giving you an idea of what we did, since it was a long process. So I am just introducing quickly the three companies. So BMD, it's a company, it's an Italian company, and we are producing products mainly for air filtering systems, but also integrating complex equipment in the defense business. Chericol, it's like a research and development unit belonging to Colorobia, which is the parent company, and they together can develop almost any catalytic system or ceramic system or pigments or chemicals in the ceramic business, and not only. And obviously, I'm just putting a line about the funding done by the Italian military. So here more details about the company, and you see about the line about Chericol, and they also have very deep experience in advanced materials, ceramics, catalysts, and photocatalysts. So we put together all the expertise we had in our companies, and we had an idea: the removal of air contaminants by photochemical oxidation with a titania catalyst. And when I say contaminants, I should specify chemical and biological agents. We will see that we did testing only for chemical agents, but from a theoretical point of view, as some preliminary results, we can say also to biological agents. So this is the background for Chericol. The company has a lot of patents covering photocatalysts active under UV, and in the previous presentation I heard about UV, but for chemical detection. In this case, it's just for activating the semiconductor, and for visible light too. And also they developed a sort of prototype unit for collective protection systems using this approach. So few more slides covering a little about the scientific background, and we will cover catalysis, nanotechnologies, some fluidodynamics, very short ideas. So what we see here, so 3 pictures, very basic ones you can find in any web search engine looking for catalysis, photocatalysis, or semiconductor business. So it's 3 different ways for showing the same project. We see the valence band, we see the conduction band, and you see from our previous studies, university studies, that there is a separation. If we have no separation, it's not a semiconductor, it's something different. If we have a significant separation, it's a semiconductor. If the separation is quite big, it's an isolator, but we are going to use only semiconductor. So we have a difference between the 2 bands, and this difference is the energy gap. That's a critical value for our research. On this top right slide, we see the same, but with the excitation by a single photon that it's able to excitate the emission of 1 electron from the valence band to the conduction band, and the energy of the photon must be equal or higher than the energy gap between the 2 levels. What we see on the bottom right, it's what we are implementing in our latest development. So we are adding some special chemistry inside the titania photocatalyst, able to reduce the energy gap between the valence band and the conduction band. I'm sorry, because some part of the pictures, like the one on the bottom right, are in Italian, but easily understandable because of the science. It's a common language in every language. So it's the same, it's showed in a different way, but we are saying about the same thing. What is really important is what is written here in the box. Oh, I'm sorry, I clicked. So what is written here in the box, titania appears to be the ideal solution because it's cheap, widely available, easy to synthesize and manipulate, low toxic to humans, and I should say to animals, corrosion resistant, and a good oxidizer. We will see why. And we see here some figures, in particular one, which is the energy gap between the 2 bands within titanium. In this case, it's 3.2 electron volts. So we need a photon with a wavelength equal or lower than roughly 400 nanometers. Here we see the actual figure, but we can say below 400 nanometers. And the physical principle we are experimenting with this excitation is the production of what we call an electron hole. So we have a virtual positive charge and a single electron, which is the counterpart. Here again, it's another way for showing always the same process, the electron hole, which is represented by H plus, and the electron, the valence band, the conduction band, the photon, which needs to have an energy equal or superior to an energy gap, and some virtual representation of a part of the chemistry that is running between the process, where D is donor, A is acceptor, H plus is the electron hole, E is the electron. So what is very important here is that we are making a sort of plasma ion, a reactive plasma ion, which is quite complex, but it's able to oxidize almost all the chemicals we have in our planet. Here, it's a similar approach, showing directly the excitation and the chemistry reaction, the formal chemistry reaction based on the titania substrate. But what is really important is reaction 5, where we see that a compound, whichever it is the compound, will be at the maximum oxidized level at the end of the process. Obviously, if at the beginning we already have an oxidized compound, we cannot oxidize it anymore. So if we have carbon dioxide, we cannot oxidize carbon dioxide to a higher level of oxidation. So this is the only real limitation we have in the technique. But we are lucky because most of the toxic chemicals we are experiencing in the defense business are not fully oxidized. So this is the synthesis of what we have till now. So we have like a combustion process, but it's not running with any real flames. So whenever we have an oxidation, we have a change of the oxidation number to the maximum possible level. And in our case, we can go to the mineral, what we say, the mineralization of the organic and inorganic material. Okay, so here a few words about why nanotech. Obviously, titanium dioxide, it's a sort of nanotechnology. We can make very, very, very small particles of this chemical. And what is the added value done by our research is that a special synthetic way for adding nitrogen atoms within the crystal lattice of titanium dioxide. And this is the special, a sort of special chemistry we are adding to the system. So probably I have in a, okay, we have here on the bottom right part, again, some words are in Italian, but easily translatable to the English, because in this case, science is again a universal language, valence band, conduction band. So adding some nitrogen atoms within the crystal lattice of the system, we are reducing the energy gap, and it means a shift to higher wavelengths. So it means to lower excitation photons. So we are saving some energy using this. From a purely chemical point of view, it's not changing so much, but from an energetic point of view, we are saving a lot of energy using this special catalytic material. What we see here in the picture, it's a sort of strange material. It's actually, it's not strange for any reason. We call it an honeycomb, and it can have some different physical dimensions. What you see here, it's like 15 by 15 centimeters, or can be 75 millimeters by 75 millimeters, and the depth can be anything from few millimeters up to few centimeters. And you see square holes everywhere in the platform. Obviously, the air it's flowing through the holes, and the catalytic material is deposited everywhere you can imagine within the active surface. So the filtration area of the honeycomb, it's incredibly higher than the regular free part area we can imagine. At the beginning, we started with the ceramic materials, and that obviously have pro and cons. Like, it's a very stable chemical material. We can use high temperature in synthesizing it and adducing some chemical stability and reproducibility, but on the other way, it's very fragile. So can you imagine in a reconnaissance vehicle, in a combat vehicle, it will be very difficult to manage in case of off-road activities. So we changed and tested some polymers, and at the end we were able to use an available polymeric mixture, and was developed on the same geometry. So it's what is written here, and we used a 3D printer for making this substrate. So it's if you touch it, you see the difference between the ceramics and the plastic. But if you have a look from a presentation, you don't see any special difference, unless that the plastic mixture it's very transparent to light, because we want to transfer the light wherever it's possible inside this special honeycomb. And obviously the catalyzer was applied using the coating technique. With the ceramic honeycomb was done like for immersion and cooking at a high temperature, but in this case the plastic substrate it's not available to survive to 500 C or 600 C. It will destroy completely. Okay, just few words about the fluid dynamics study that we did with our capabilities and using the University of Rome Tor Vergata as a consultant. It's you see a very synthetic image of the air approaching the different blue layers, which are the honeycomb you saw in the previous picture. Obviously, we have outside a matrix of LEDs that are providing the light, because we don't have to forget that our system is a photocatalytic system. So we are using light to generate electrons, and electrons holes to make ions and to oxidize the chemicals. And for verifying what we were able to do, we did some chemical tests in many laboratories. And one of the main testing chamber, it's what you see in the left picture. So you see a bench, a dedicated bench, a patented bench, and most of the intelligence, electronics, and fluid dynamics, it's inside the doors, and the real photocatalytic reactor, it's what you see on top left, right, that is enlarged on the right part, so you see a part of the testing system. So this is a picture of the software that was used to control. I don't want to lose time in describing the system, but anyway, you can imagine we have a dosing system for the chemical. We have a diluting flow for adding the wanted air to have the final concentration we want. The photo, it's the photoreactor, and at the end we have the dedicated analyzer depending of if it is nitrogen oxide, if it is a VOC, we are using GCMS. Can be a Tedlar or another material bag, or can be a loop using GCMS or GCFID, depending on the chemicals. What is really interesting is to show some data that came from the early chemical tests using nitrogen oxide. Luce off means no LED light. Luce on means LED on. So what you see on the beginning is the testing concentration. So no change is appreciated. So the material is totally inert. We switch the LED on, so we see an immediate decrease of the concentration of the nitrogen oxide. Obviously, we are oxidizing the nitrogen oxide to superior oxides, nitrogen oxides. And we switch the LED off, and immediately the concentration is reaching again the maximum. And so we tested in this way the ability to oxidize and nitrogen oxide. So this is what we used from the beginning to the end to evaluate as a sort of internal quality check and quality development process for seeing if the catalytic material was able to do the task or not. And here some more data about the experimental apparatus, the drawings, and the detection system that we used for the experimental chambers were inline FTIR, GCMS, and dedicated sensors. In the next slide, probably you will see the outcome using FTIR. And we used FTIR, inline FTIR, because it's quite fast, compound specific way for detection the concentration in almost real time coming out from a system. And this is the data I was just assuming before. So on the left side, you see the concentration in milligram per cubic meter of dimethyl metal phosphonate, which is commonly used nerve agent simulant, and which has also some toxic properties. And what you see on the huge peak on the left, it's the conditioning step for the full equipment charge, and the LEDs are off. So no energy is provided to the photocatalytic system, so we can see all the DMMP coming out from the system. In this point, we switch the LED on, so we are providing energy to the catalyzer. And so the catalytic system is starting to make ions and to burn all the DMMP to elementary mineral compounds. So the concentration is sharply decreasing to 0 and staying constant for roughly 2 hours. After some 2 hours, some more leakage of DMMP can be seen at the exit of the filter. So we switch the LED off, and we can see how the signal, the concentration of DMMP is increasing slowly. So we can say that for this time, no DMMP was coming off from our prototype filters. So at the end, we can say a few things about what we said. So, and we were able to define what is the elemental unit. In your mind, it can be like the honeycomb. The elemental filtrating unit which is not a single honeycomb, but it's a combination of more honeycombs in a serial way, and with the power supplies, ventilation system, and metal structure for ruggedizing the system. And at the end, we were able to develop the working prototype. So this is the conceptual 3D drawing of the filtration units, so more elemental units all together. So you can imagine the air is entering in this place and it's going out from this place. Not showed here is the lightning system, which is a LED matrix able to provide sufficient energy to start the photocatalytic process all inside the elemental units. And on the left side, you see a conceptual 3D drawing for the working prototype. And on the right side, you see a real picture from the rear view, from the lateral view, actually, of the prototype. For one side, there is the entrance. From the other side, there is the exit. And obviously, we are closing the presentation with expressing our gratitude to our companies that laid us in giving the activity, and also to the Italian Ministry of Defense, in particular, Segretariato Generale della Difesa, and in this case, Direzione Armamenti Terrestri, that were able to provide us funding for the project. And obviously, I want to thank all the team members, because at the end, more than 30 people worked all together in developing the prototype. So this is the end of my presentation, and should you have any questions, feel free to ask.
Thank you, Dr. Pincerelli. I see if any questions from the audience. No any questions from the audience. Thank you for your presentation. Frank, any question?
I have one question. I missed the wavelengths for the LEDs. Can you?
Good question. At the beginning, the preliminary system was working in the UV, so it was roughly 390 nanometers, and the actual system is running close to 450 nanometers. Obviously, it's a narrow band LED, but we can focus deeper and deeper the wavelength, but we don't want to use just a single wavelength. Our LEDs are spreading a full spectrum.
Do you expect that even sunlight would activate the reaction?
Can you say again? I missed the beginning.
Do you expect that even sunlight in summer or so would activate the reaction?
Absolutely, yes, because of it's more energetic than the visible light. Yes, absolutely. Obviously, our system is not able to capture any sunlight because it's sheltered by metal, and because it's something that is dedicated for the military application. But obviously, UV light, sunlight can activate the photocatalytic process. Absolutely, yes.
Okay, thank you.
No more questions. Thank you, Dr. Pincerelli. And,
thank you, Professor Gaudio. Thank you to all. Thank you to all.
Thank you. I see Dr. Carcano. I just to thank Dr. Carcano, this president of BMD, for supported these events. Is our platinum sponsor. I don't know if Dr. Carton, if you say some things, pleasure.
I wish to thank you for your attention. First of all, this session was dedicated to our R&D project we just completed a few weeks ago. And again, as Luca Pincerelli said, we also are very thankful to the Italian MOD for supporting us on this project. And future possibilities are open for additional investigation. that we will investigate in the near future, and of course share information as soon as possible. Probably tomorrow we will have more time to introduce our company and what we are doing so far, and for the time being I think that's it, and tomorrow we will give you a better snapshot on what we are mainly focusing our days.
Thank you, and thank you again for support our conference. It's very gratifying. Okay.
Thank you.
We arrived to last presentation, and we close this technical table. And I would like to thank to all the speakers for their interesting presentation. The session with Chair was very full of very interesting speeches. We went from the detection of biological, chemical and explosive agents. We have seen new detection systems and techniques that are very interesting for civilian community. The hope is that today's presentation will give rise to new collaboration and a new idea for new research activity, collaboration, and eventual network for proposal requests for fund under the next framework of a European Community FP9 that started just in few months, the next few months. We hope is that the next conference can be held in presence, and we hope that pandemic situation will close very early. And this is the goodbye, arrivederci to the next international conference of the SICC series. Thank you to all. I don't know if the other chairman want to say something. Frank, we don't hear you.
Well, Pasquale, thank you for hosting this conference, this interesting conference. But I must point out there are a couple of sessions this afternoon still, so we have some hours ahead of us. But thank you.
Thank you.
Thank you, Pasquale and Frank. I think this has been very interesting, and I think quite exciting for encouraging us for improving the technologies and science. And I think that that this is key for fighting against this kind of episodes that the pandemic has demonstrated. It's not something, it's not fiction. It's something that it's unfortunately it's real. So I think that demonstrates the need of this kind of conference, and how it's key for Europe and for the world. So thank you very much. It has been a pleasure to be here.
Pleasure for us.
Thank you very much to our precious chairman. I would like to remind all of you that this afternoon we will have session 3 and 4 of the conference, and tomorrow we will have the plenary session and the poster session in the afternoon. So I hope to see our attendees also this afternoon and tomorrow. Please don't miss the plenary session tomorrow as well. And now just feel free to visit our virtual reality area, our sponsors desk, and all the information that you can find there. Have a nice lunch break.
Thank you very much. Thank you.
Bye-bye.
Bye-bye.